So it gives me a really great pleasure and great honor to introduce Victor Shoup. So Victor Shoup is a professor at NYU. I had the pleasure of learning a lot from him in my time there. And Victor's background is in computational number theory and algebra. And he really, his work really enriched the field of crypto by introducing a lot of novel ideas, especially at the algebraic level. So one of the main themes of his work is that even simple algebraic structure that comes out in crypto systems, like based on DVH or RSA, is already enough to construct really advanced cryptographic primitives, efficient cryptographic primitives like CCA encryption, signatures, password authenticated key agreement, and many of the things that we'll actually hear about today. And I think this work, the reason I really like this work is that it beautifully combines ideas from both computer science and mathematics. So for example, and point of views from these topics. So for example, it uses the algebraic structure that comes from crypto systems, but then sees this algebraic structure as producing something like universal hash functions that come from theoretical computer science. So these ideas, these two areas are really deeply intertwined in this work. Victor has also done excellent and wonderful work on putting cryptographic definitions and proofs on a more solid mathematical foundation. So for example, he formalized the idea of game-playing proofs, something that is inherent in all of our papers pretty much, but sometimes we use it in a bit of a hand-wavy manner, and this really puts it on solid foundation. Also formal models of key exchange, and more work recently has been working on formal definitions of composable security. Not anymore. So not that recently. Victor has also been working on the practical aspects of cryptography and making sure that this beautiful theory can be used in the real world. So he's the creator of the NTL, the number theory library, which implements a lot of the number theory and algebra that's needed in cryptography, but also more broadly. And more recently, he's been working on implementing fully homomorphic encryption and showing that it's actually something that can be usable and practical. He's also involved in designing ISO standards, so making sure that the cryptography that's out there in the real world is secure. And Victor is also an author of a textbook on computational number theory and algebra. That's a textbook that every cryptographer should own. It's a really wonderful resource. I use it all the time. And he's working on a much anticipated textbook with Dan Bonnet on cryptography. I just heard news that there might be a partial release coming soon, so this is groundbreaking news. Something will come soon. And so we're all very excited and waiting for this. So without further ado,
okay, thank you very much.
And it's an honor to be invited here to speak with you. I'm going to talk about some work I did some years ago, and I haven't done too much with it since. But what I found, I thank Tal for inviting me, because I haven't really, and Danielle, and I don't know who invited me. I had the conversation with you. I was just thankful in general that I actually went out and, to prepare for this talk, went out and read a lot of recent papers on this area, which I had no idea actually that it was such a rich and vibrant. No, it's true. I didn't really know. So I've been working just on writing C++ code for the last 2 years, so and writing textbooks. So a little bit of background, not too much. I don't want to talk about definitions and history. Cynthia probably covered a lot of this material in greater depth. So, it's hard to imagine a world without cell phones and CCA secure encryption, but there really was a time when we didn't even know we wanted them, right? So now, right? So now we know that we want and need CCA secure encryption, and really back in the day, I mean, people were making these definitions and nobody knew if it was actually important or not. I mean, it wasn't clear what, like, the practitioners didn't realize that they should want this, right? And then it took a while. So Nahor and Young had an initial definition of what now we call CCA1 security. Dolev, Dwork, and Orr did some more work and related it to concepts of non-malleability, which wasn't clear at the time how these things related. Rakoff and Simon did some work formalizing and giving some initial designs for what we now call CCA2 encryption. I put Belar and Raghavi up here too, because they were the first ones really using the random oracle model, which kind of, they both recognized the need to make this stuff practical and showed how to do it using at least the random oracle heuristic. So the stuff I'm going to be looking at is all stuff related to these two papers from '98 and 2002. And then, so let me just jump to the outline. I'm not big on outline. So I'll do some definitions and examples of hash-proof systems. So these are kind of in retrospect, we kind of realized this was kind of the right way to look at what we were doing and to generalize what we were doing back in '98. And some examples. I'll do, I haven't talked about this stuff for years, so just for old time's sake, I'll walk through some constructions and proofs based on this old stuff, and then hopefully I'll be able to spend a relatively significant amount of time talking about more recent work, even from this year, in fact, on password authenticated key exchange and applications of what we call hash-proof systems. And maybe also about, since we're talking about historical papers, in terms of papers, I have to say, so this paper on hash-proof systems appeared at a conference, Crypto or Eurocrypt, I don't remember which one. And then we never published a journal version. It's on ePrint. It's very long, and when I actually had the unfortunate experience of going back and reading parts of this paper, which I don't know if you've had that experience, reading your own stuff from a long time ago, and you said, God, this stuff is really hard to read. But
We had the experience of reading that.
huh? You actually did, yeah. Oh, yes. When I was reading through your paper and I saw that, man, you guys, wow. Yeah. You actually read it, yeah. So, but not many people actually did. But you're one of the few who I think actually did, because I won't name names, but I mean, and I don't blame anybody, because it was like so densely written, and some of the more important stuff, which we probably didn't realize was important at the time, was like buried on page 58. In some mathematical language that we made up and nobody understood. And so there's been a certain amount of reinventing the wheels over the year, but that's okay. So let me just start out with definitions. Everything I say will be like Daniel was saying, simple ideas. It's simple high school, well, not high school, but elementary linear algebra. Huh? Well, not an American high school anyway, maybe. In Israeli high school, you probably cover some of this stuff. But. So we start out with the usual NP language scenario, right? We have some ambient space X and some language L, and L is characterized by relation with witnesses. So the language consists of all elements in the ambient space for which there exists a witness, right? So the set X is the set of words or statements. Language is the set of true statements or theorems. W is a witness, and R is a relation that defines the language, right? Okay, nothing new here. Moving right along. So now, to define what is a hash-proof system, I'll give some, if you haven't seen this before, I'll give some motivation for the terminology and such. Right now, I'm just going to lay it all out. So there's a key generation algorithm. So I'm going to call these today, other people don't always call them this, a public key and a secret key, so just like kind of an asymmetric setting. The secret key defines a hash function. So the hash function's domain is the set X of all statements, and the output space is the set pi, which we'll think of as proofs. Generally speaking, it'll be an abelian group. It doesn't have to be, but for almost all the interesting applications it is. Yeah, okay, so it's a hash function that uses a secret key, and it maps elements in X to proofs. The public key, what it does is it allows you to evaluate the hash function H you don't have to know the secret key, but you can evaluate anywhere in the language if you know the public key and a witness. Okay, so it's kind of like you have, maybe you can think of SK as a trapdoor. I'm not sure if that's the right language, but you have a couple of different ways to evaluate the hash function, either using the secret key on anything in X or using the public key on the language with the witness. Those are your two options. Later, I'll talk about some other options, but right now, this is the only options we have. And then there's this notion which I'm changing and simplifying terminology and kind of like adapting what people are using nowadays. So I'll just call this smoothness. Smoothness just says that if I pick a secret key and you pick something in X that's not in the language, then even if I show you the public key, you can't guess what the value of the hash function is on this point, right? So the value of this hash function using the secret key on X should be uniformly distributed over all possible outputs, And even if you see the public key. So the public key doesn't help you. So with the public key and a witness, you can evaluate in the language, right? So here's all of X, and here's L and X. So if you have the secret key, you can evaluate everywhere. And if you have the public key, you can evaluate inside of L with a witness. But outside of L is a mystery, right? Which you only know if you know the secret key. So I mean, the reason I guess you would call this a proof system is that it has, you can use it. This is not really the way you would, well, you can use it this way in some applications. It's kind of a natural thing to do. It's not necessarily the most useful thing to do. So say we have a prover and a verifier. The prover has something in the language, X, with a witness, and he wants to prove to the verifier that this is the case. So somebody, maybe the verifier, maybe it's kind of a system parameter or not, but somebody should generate a public key secret key pair, and the prover takes the public key, and he evaluates the hash function using the public key and the witness to get his proof, and he sends that back to the verifier. And then the verifier doesn't know the witness, but he knows the secret key, so he can check whether the proof corresponds to the correct hash value. Yeah? Does that make sense? So, and smoothness, so what property, as a proof system, what does this have? Well, soundness is guaranteed by the smoothness property. Yeah? If the prover tried to prove something outside of this language, then he can't, since this, even knowing the public key, the correct value that the verifier is going to try to compute here is independent and uniformly distributed over the set of all possible proofs, right? So he can't possibly guess it. So that's kind of where you get soundness from. And when I wrote this slide, I tried to come up with other kind of properties that such a proof system, I mean, soundness, okay, whatever. It's not much, right? There's more things you want from a proof system. I'll talk about this more later in the talk. We'll come back to this. You can actually use these things in real life proof systems, and people do. Depending on the setting, you know, it's not zero knowledge or anything, but under the right circumstances, can be witness indistinguishable.
It's statistical zero knowledge. Honest verifier.
No, honest verifier statistical knowledge. Well, wait, only if it's witness indistinguishable. That's the only thing I know for sure. I haven't thought about what you're saying.
I can simulate.
No, only
How?
Only if you have hard on average language, right? If X is worst case, I mean, there is no pseudo-randomness.
What?
If
If
you have a
X is worst
distribution, yes
case?
or no.
No.
If it's in the language, I'm.
SK myself.
Oh, the verifier knows SK. So, I see. So it's okay. All I thought about is witnessing indistinguishable.
It's honest verifier knowledge too.
Statistic.
But it's only honest verifier. Well, it's actually only honest verifier witness indistinguishable too, because there's an issue that can come up where you have to trust this public key in some sense. And that's actually a point that comes up in some protocols later that I'll talk about.
So in particular, the only languages you can do this are ones in statistical ZK, right? The only languages for which you can construct a hash proof system are, I mean, you cannot construct them for any.
Oh, I see. So I see that. Okay. I'm not an expert on this. I actually haven't thought about these things that way. So that's, I'm glad other people have, because I haven't. Okay, so let's look at the kind of the simplest possible example, kind of the original hash proof system, as it were. We'll look at the decisional Diffie-Hellman problem, and I'll set this up in a funny way that, you know, I guess back in 1995 you wouldn't have been thinking of these things this way, but now people do. So we have a group of prime order Q. P is a generator for the group. Just to confuse everybody here today and to keep you on your toes, I'm going to write everything additively. So even if you've seen this all before, it's all going to be fresh and new, right? It's all going to be additive. So and we can pretend we're mathematicians who know something about elliptic curves, right? And then we can pretend these are points on an elliptic curve that we're using here to be sophisticated. But actually, I just find that with all the linear algebra that one uses in this area, that it's just easier to work additively. So we're going to have these scalars, and I can multiply the scalar by this point P, and I get an element in the group. So I try to be very consistent with, 'cause I have a hard time keeping track of things myself. So I try to be very consistent with fonts here. So lowercase is always a scalar in ZQ. Uppercase is always an element of the group. So we can have two elements of the group, x1, x2, which we could write like this. And then we have vectors, which are always in boldface, yeah, like this. A vector of groups, a vector of scalars, right? And we can write that as, think of this as the scalar vector x times the point P. And using this, you see that the set of pairs of group elements can be viewed as a vector space over the field ZQ. Okay. So next, we pick a single vector in this two-dimensional space, L, and we look at the subspace generated by this vector. So that's a line in two-dimensional space, right? And that's our language. So a witness is just the scalar that maps the vector L to the vector x. And our language is just the set of all vectors which are on this one-dimensional in this one-dimensional subspace. Okay, yeah, so the language is just the subspace or the line spanned by L. And then here's what a Diffie-Hellman tuple looks like in this alternative universe. So we have our line, our point L, our vector L, rather, our vector L. And then we take a scalar W. This is in our language, W times L. We write it out as a matrix. Say L is L1, L2. The lower row is WL1 and WL2. And if we say, well, say L2 is V times L1, then we get this tuple L1, VL1, WL1, and VWL1. So it looks a lot more like G to the X, G to the Y, and G to the XY, right? So that's where Diffie-Hellman comes in. So these are the Diffie-Hellman tuples, and right, the decisional Diffie-Hellman assumption that it's hard to distinguish random things that are in the subspace from random things that are out of the subspace. So now we build a hash-proof system for this language. It's very simple. We pick a secret key, which is a scalar vector A. So it consists of the two coordinates A1, A2. We take now an arbitrary x, right, in the ambient space of pairs of group elements. And the hash function using the secret key is evaluated by just taking an inner product. So this is so you think of all the vectors here are row vectors, and then this is a column vector. So I write x times A transpose. That's just an inner product, right? So if this would just be A1 times X1 plus A2 times X2. So it's just an inner product. So that's how you evaluate the hash function on the secret key for an arbitrary point in the vector space. The public key, it's not always as simple, but usually it is. The public key is just kind of like taking this inner product and giving you a sample, right? So you take this generator for the subspace L, and you compute the inner product with your secret key, and this is the group element now, right? And that's your public key. So I've shown you how to evaluate this inner product using the secret vector on the sample point L. So now you should be able to compute this inner product on an arbitrary element in the subspace spanned by L, right? So you take x and w now, so x is supposed to be on the line, so it's w times L. And then we want to compute this inner product, right? The inner product of x with A. We don't know A, but we know big A, right? So big A is this guy. So, and this is just a matter of moving parentheses around, right? So x is w times L, and then thank goodness associativity holds here. So we can write w is L times the inner product of L with A, and we get w times A. Yeah. So given the image of this linear map A on the generator L, we can compute the image of this linear map on anything in the subspace spanned by L. Smoothness. So this shows, right? So smoothness. Now you take this point L. And look at, you have this inner product, right? So we can look at this as a matrix vector product where this row is the generator L. And this row, say, is the vector x, which represents a point off the line, right? And and this row times this column is the inner product, right, which corresponds to the public key, right? That's this guy. And this row times this column is the value of the hash function at the point x, right? And this is off the line, right? So to see that we have smoothness here, it's just a matter of seeing that, okay, so you think of L and x as fixed, and this A is kind of this random secret, and this vector, this pair of vectors, when you put them together, you get a 2 by 2 matrix, and it's full rank. That's all that's happening there, right? So because we're assuming here that x is not in the span of L, that means these two rows are linearly independent, which means these two columns are linearly independent, which means that when you take the inner product here, you just get, it's a one-to-one linear map, right? So the outputs here, if this is random, the outputs here are random, and that's it. So even if I give you pk, this is the hash of this value x will look random to you. So this is just kind of a weird variation of kind of pairwise independent hash functions. Oh, and I was going to say one other thing. So that's kind of an interesting way to look at it, perhaps. And I just thought another way to look at this is if you think of, if instead we took an inner product here on the left, say a row vector times this, we would get a random linear combination of L and X, right? Which also is just another way of looking at the random self-reducibility for DDH, right? So if I take a random linear combination of the point L and the point X, then I'm going to get, if X is in the span, then I get something else that's in the span. If it's off the span, then I get something in the big space. So I guess just moving this vector here over here changes the story a little bit. So here's like the one thing in our paper that I feel like was buried on page 57, and I wish more people had seen. So a simple generalization of this is that if I take a set of, so I have, say, now work with longer vectors of, say, dimension n, and I take some set of generators, so these are all just vectors in this bigger space, and I look at the vector space generated by them. Then this all works just by adding indices to everything. So the secret key is still just a single random vector, and the hash function using the secret key is still the same. The public key, though, is basically just taking the inner product of the secret key on all of the generators. And then if I have something in the space spanned by the generators, so that would be a point that looks like this linear combination, right, of the generators, and I'm supposed to know these witnesses, these WIs. So again, it's just a matter of moving parentheses around. If I want to compute this inner product with this point x and the random vector a, then I'll just expand it out. Here's x. It's a linear combination of the L's. And then I can move the parentheses around to say it's a linear combination of the public key elements. Yeah? And I just evaluate it like that. So if I show you how to evaluate this function on the generators, then you can evaluate the function on any point that's generated in the span of these generators. But draw the same picture with matrices, on the previous slide, you'll see that if I give you a vector that's not in the span, then even if I give you these points here, the public key, the value of the hash function outside of the subspace will look random. So here's an example of this. The decisional linear Diffie-Hellman problem, DLIN, can be set up in this way. So here we can take 3 generators for the group. And then I'll define 2 vectors, P1, 0, and P3. And the second vector consists of 0, P2, P3. And then you look at the subspace spanned by these 2 vectors. So that'll be all elements of the form W1L1 plus W2L2. You plug it in and expand it out, and you see that the first coordinate is of the form W1P1. The second form is of the form W2P2. And the third is always of the form, W1 plus W2 times P3. So that's exactly, the set of elements corresponding to the decisional, the DLIN problem, decisional linear problem. And this generalizes from 3 to any number. So, and then because of this, you can set up hash proof systems for the DLIN language as well. In our 2002 paper, I guess we didn't talk about this stuff that much. We mentioned it, but then we mostly found it interesting that you could set up hash proof systems for other groups that didn't have this simple linear algebraic kind of structure. So for quadratic residues, mod n, and also for this Pallier subgroup, the nth powers in Zn star squared that Pallier used in his encryption scheme. And the funny thing is, in retrospect, I guess some historical evaluation of all of this is perhaps that this simple linear algebra stuff has probably been much more useful in doing new things. This stuff has been useful, mainly in just extending known results to say, but we can also do it under these complexity assumptions. But and you guys did a lot to clean it up and make it much more easily applicable to wider settings. Okay, so I won't really talk about this stuff much more today. So I'll talk about, like I said, I'll begin the talk with just some reminiscing about old encryption schemes from 20 years ago, and then I'll talk about newer stuff. So the applications of public key encryption. So the generic way to use this framework is like this: we have a hash proof system for a language, and then we need some additional assumptions. That it's easy to generate things in the language along with the witness. So I'll call this algorithm iGen. Here we need a decision assumption. So we need to say that it's hard to distinguish things in the language from things outside the language. So a randomly chosen thing in the language should be hard to distinguish from a randomly chosen thing outside the language. And we'll need to assume our proof space pi is a group, an abelian group. So the public key and secret key for the encryption scheme will just be the public key and the secret key for the hash proof system. Here's how we encrypt a message. We generate a language element along with the witness. We evaluate the hash on the language element using the witness. And this is an abelian group, which we're writing additively here, so we're going to add the message to that, right? And then we're going to output the pair XE. So X is the language element, and E is this kind of encryption of M using the hash proof as an encryption. So then to decrypt, you just subtract. You take the element E. You don't know the witness, but you know the secret key, so you can subtract off this hash value, right? And to get the message back. So here, let's do one proof, just for have a proof. So here's a proof of semantic security. So this is just semantic security. So the game is the adversary submits two messages, M0 and M1, to the challenger, and here's what the challenger does. He chooses a random bit. He encrypts the message, MB, so this is just the encrypting MB, and then he outputs the ciphertext, right? And then the adversary sees the ciphertext, and he has to guess the hidden bit B, right? That's the semantic security game. So we want to prove that his probability of guessing the bit B is negligible, or negligibly close to 1/2. So we just changed the game a little bit. So in game 1, instead of encrypting the message M sub B using the public key, we encrypt it using the secret key. It's not what the usual encryption algorithm does, but we'll just go ahead and do it anyway. It's just a game. So that's game 1. Does the adversary's advantage change? Not at all, right? Exactly the same distribution. Then, here's where we play our DDH card, or indistinguishability card, right? So instead of generating X in the language, we just generate outside the language. We don't need the witness anymore, right? Because we did in the previous game, we switched to using the secret key. So now we don't need the witness, and we just go ahead and do this. And I think that's the whole proof, right? So to finish the proof, then there's no more games. So to finish the proof, you just say, well, by the property of soundness, right, the bit is perfectly hidden, right? Since we're outside the language now, in this game, this value here, even given the public key, is perfectly random. So this is a perfect one-time pad, right? And so whatever advantage the adversary had in the original game, he has here. But here, there's nothing. So whatever difference there was has to be explained by the changing from game 1 to game 2, where we switched from inside the language and outside the language, right? So if you could distinguish here, we would have a way of distinguishing the language from outside the language, which we're assuming you can't. So that's the proof. So let's go now to, this is just, right. So this is just plugging in DDH into this. And we get, so the secret key is a vector A, so 2 random elements in ZQ. The public key, so there's a public parameter here, L, which could be part of the public key or just set publicly once and for all. So it's a pair of kind of random group elements. The public key itself is just the group element A, which is just this inner product of L with the secret vector. And then encryption, just plugging in, we take a witness and then we compute. So the witness is just a random scalar, and then the group element is just a random point on the line generated by L using the scalar. And then we encrypt our message like this: Y times A. That's the W times A is just the hash proof using the public key, and M is our message now. It's a group element, so it's a capital M. And then our output is the vector x, that's 2 group elements, and the third group element y. And the decryption then is, again, just taking y and subtracting and using x to applying the hash function to x, which is just this inner product. Yeah? So now we have an encryption scheme that has whose ciphertext consists of 3 group elements. It's kind of like El-Gamal, right? But it's actually worse than El-Gamal, right? El-Gamal is just g to the x, h to the x times m, right? So we've gone backwards. There's no real point to this. Now we've just have 3 group elements instead of 2. So, but it gives you a different way of looking at things, which is, as you know, is useful. But so then we can talk about how to build CCA secure encryption schemes, right? So let's just identify this last scheme, pretty much just like plain old El-Gamal, is clearly not chosen ciphertext secure. And there's many different ways to see it. I guess the way I'd prefer to look at it right here is just to say that, well, here's how the decryption algorithm works, right? The adversary gives you an arbitrary group elements x and e. You don't know if x is in the language or outside the language, but you go ahead and compute e minus the hash of the secret key, right? But that already leaks information that to the adversary that wasn't available to him in the semantic security game, right? In the semantic security game, he just saw the public key for the hash proof system, and he saw nothing else, right? And the assumption was that just given the public key, the value of the secret key on any other point looks random. But here, he might get to see the value of the hash function on points outside the language. And I mean, for particular schemes, that might leak the entire secret key, right? And it does, at least information theoretically, it does. And certainly it breaks whatever assumptions we're making about this thing as a hash proof system, right? So without some control over how the adversary gets to query this decryption oracle, this will leak information about the secret key, which will break it, right? So the solution, or one solution maybe, is just, ciphertext should come with a proof, right, that X is in the language. Then this won't be a problem, right? So then we can build a NIZK and do all this stuff, right, or use random oracles and do something else. But of course, we don't want to do all that. So what we're going to use is the only thing we know. Everything is a nail, and all we have is a hammer. Is we're going to just use hash proofs to do this, right? So we're going to use hash proofs to provide a proof that this thing is in the language. Right, so here's the first attempt. Of course, most of you know the end of the story. So, but the first thing you would try is kind of stupid, even a priori. But okay, another one not to try stupid things. So we just take the old system, and we just add another public key secret key pair. Right? I said we could do proofs with hash proof systems, right? So let's just use one, right? So we'll prove that X is in the language, right? So we'll just add a proof, right? And then this guy will test it. I said you could do this, and so let's just do it, right? So I'll just add a second pair of keys, and the encryptor is going to supply proof that X is in the language. It's going to test it. So what can go wrong, right? So, but okay, the proof of security fails. Let's see why. So if we go back and just try to retrace our steps, right? The proof. Let's just try to see if we can follow our nose here. What goes wrong? Well, the first thing we did was to remember, just doing 2 steps at once here, right? We replaced the hash proof here by one that uses the public key by the secret key, right? And then we jumped outside the language, right? Good, fine. But what do we do with this guy now, right? He needs a witness, right? So the only thing I can think of to do is just, okay, let's just do the same thing we did before, right? I don't know. Let's just try it, right? But that of course doesn't work, right? Because, again, we've blown the soundness, right? These hash proof systems are only good for their one time. You use them once and you have to throw them away, right? Once I evaluate using this secret key prime on a value X that's outside the language, which is what I just did, right? I mean, my simulator did this, right? And so now all bets are off, right? So we need, what's in the literature or what's in the parlance is, simulation soundness, but just one-time simulation soundness. So we need a way to generate a fake proof that doesn't compromise soundness, right? So that's all we need. And in fact, we can do that easily. Just, I think it was Amit who said, so this quote from the movie Contact, which is why build one when you can, what government contractors' favorite philosophy is why build one when you can build 2 for twice the price. So that's what we'll do. We'll just use 2 hash proof systems and hopefully something good will happen, right? So, okay, I'll try to define this. I don't want to get too bogged down in it. There's a couple of different ways to do it. But the basic idea is we want something like hash proof systems, but it gives us kind of one-time simulation soundness. And in retrospect, over the years, I've kind of figured out the best way to do this is probably the cleanest way is using some kind of tag-based kind of. So a tag is, just think of a tag as like a a context in which the proof will be generated and verified, right? It's kind of the name of the, right? On Monday, this is the proof I did on Monday, and if you check Monday's proof, it'll check, right? And here's Tuesday's proof, that's another tag, Tuesday, and if you check it on Tuesday. But if you take Monday's, but the proof I ran on Monday, you can't, verify it on Tuesday, or something like that, right? This is the tag or context or the name, a label sometimes it's called, right? So as before, we have a secret key that maps elements in our big set X and a tag to a proof. And then our public key works as before. If you have something in the language with the witness, and you take any old tag, then you can evaluate things as before. So, right, so there's just this extra label or tag attached to a proof, right? You need some way to identify these things, and this is kind of a convenient thing. So 2 smoothness is kind of the one-time simulation soundness. So it says that if you take any 2 things outside the language, they can be the same. They don't have to be different. What's important is the tags, actually, in this particular way of setting these things up. You take any 2 tags, and if they're different, if the tags are different, then you can say the following, that the hash values using the secret key on x1 and x2 are uniformly distributed over all outputs, and all 3 of these guys are independent. So even if I give you the public key and I give you the hash on x1, the hash on x2, there's a typo here. There should be tag inputs into here. Okay, so here tag T1. Yeah, this should be T1, T2. This should be T1 and T2. Right? So you can formulate this just without the tags and say x1 and x2 have to be different, but it's in many applications convenient just to have this with just tags. And here's the easy construction, right? You just actually do 2 and you kind of tie them together, kind of like using, some basic idea from universal hash functions kind of idea. So you have 2 secret keys. Just you start off with not any. So this construction only works for these kind of subspace hash proof systems that I talked about. So not just DDH, but any kind of higher dimensional subspace problem. And also other group-oriented problems. It doesn't work for, I don't think, I haven't convinced myself one way or the other that this particular construction doesn't work for other examples, but certainly for all of the group-oriented and vector space-oriented hash proof constructions, what you just do is you just take 2 secret keys for ordinary hash proof system, and then you use your tag. I'm assuming here that so for the vector space version, T is going to be viewed here as a scalar, as an element of ZQ. And so I'll just compute the hash using the first secret key applied to X plus T times the hash of the second key applied to X. And that's it. So that's how I define my 2 smooth hash system for this. And now, in the way it's defined, of course, you can see using the public key for the hash system. I know I have a public key to work, so it just looks like this then. Right? So there's nothing new there in terms of how you evaluate the public version of the hash function. You just use the same thing. So that's it. And like I said, it doesn't work. I don't know if it works everywhere, but it certainly works for any subgroup type problem or subspace type problem. Here's for DDH. For DDH, let's see. So we want to show smoothness, right? So the construction gives you. So we're starting out with this 2 vector L, right? This length 2. That's what this extra width here is supposed to denote. So, and here's a matrix. So if you look at what this matrix is evaluate, this is L inner product B. That's public. That's one public key. Maybe that should be PK1 and PK2. Okay, more typos. This is L inner product C. That's a second public key, right? And then here's 1x. He's not on the line. So here's the hash function, x inner product B plus T x inner product C, right? This guy times that guy. That's the value of the hash there. And then another point here, okay? And it doesn't, and I'm assuming here that x and x prime are both of them are not on the line. They may be equal, they may be not. What's important is the fact that the t's are not equal. And then it's easy to see that this is just a full rank 4x4 matrix. I mean, you have to stare at it a little bit, but it's not hard. So this is a 4x4 matrix. This is a random length 4 vector. So when you hit a 4x4 full rank matrix with the random vector, you get a random vector out, right? So even if I give you pk, so pk looks random, pk prime looks random. This is h2, right? So this is the composite hash function. So even if this looks random given these two guys, and this guy looks random even given all three of those two guys. So that's the too smooth with the DDH. So here's a second attempt that works now in the kind of the general setting. We have so here's the plain. So this is kind of the general setting using hash proof systems to do encryption. Here's the semantically secure version, and then we just drop in all of the too smooth technology here, right? So here's our second public key, secret key pair. Our proof, well, we need, okay, so somehow, and this is where I won't go into the details, right? There's this, so to actually prove that something is CCA secure, you have to, well, figure out what definition you want to use. Actually, if we just did tag-based CCA2 security, this T would already be enough. But if you want to hit the classical definition, you have to use some kind of collision-resistant hash function. Where's the only target collision-resistant hash function, right? Or a woof. Suffices. And so the output here, the ciphertext is X and E, and this proof, so you have to like bind it all together, and that's where you get your T from, and that's what you plug in for your tag in our too smooth hash proof. And then the decryption, again, we just add the proof and do the test, right? We have to, again, evaluate this hash function to get our tag to kind of make sure things are non-malleably glued together. So you can't take, one X and one pi or one E and combine, mix and match in different ways. Just make sure kind of everything fits is non-malleably bound together. So this works, and kind of you can see why, right? Since we have one-time simulation soundness, seeing one proof doesn't help you do anything else, but that's it. So here's the example using DDH. So here's the plain worse than El Gamal scheme, right? So then we just add two extra secret keys, two extra public keys, the proof, and the check, and that's it. So that's what's called Kramer-Shoup encryption, I guess. There's been a ton of work done after this. I hope nobody here is upset. So Kurosawa and Desmond had a great idea to notice that you could get rid of one of the one smooth hash proof system you could just do away with. And then these guys actually noticed you could actually get rid of the too smooth, not exact. So you could get rid of, you could make the too smooth construction a lot simpler. And Hofheinz and Kiltz actually did some work, and there was some follow-on work by others who showed that you could simplify things. And also, the one thing that's probably, there's a couple of things. So all of these things give you more efficient systems. All the improvements come by looking at schemes kind of in a hybrid encryption model, where you have a public key part to kind of encapsulate the symmetric key, and then you have a one-time authenticated encryption to kind of encrypt the actual data. And this gives you a certain, using this, and this is what Kurosawa and Desmond and all the other guys did. So they were able to exploit this and get things that were, instead of 2 times more expensive than plain El Gamal, 1.2 times more expensive than plain El Gamal. But and I even worked on, like it was mentioned years ago, I worked on some standard committees. I've got all of this stuff, not all this latest stuff, but some of this stuff put into an ISO standard that, of course, nobody uses, right? Any of this provably secure stuff, even though it's like 25% slower than ECIES, for example, right? Why? Because it's 25% slower than ECIES, right? And random oracles are practical, right? So I don't know what this says about our field, right? So I was just talking to Dan the other day. There's a whole, it's cool work, but there's like now a trend, not in this area, but in a related, people are looking at tighter security proofs, right? For like practical schemes, right? Which are now, these practical schemes are maybe like 20 times slower than plain El Gamal or something, right? So I mean, unless you can just prove ECIES itself is secure under weaker assumptions, nobody's ever going to use any of this stuff. But it's still fun to work on, so anyway. And random oracles are practical. It's always good to know. But so going back, looking at this kind of, let's call this now, I guess we can call this classic Kramer-Shoup. What's been interesting story about it, though, over the years is that actually, even though it's a little bit less efficient than some of these hybrid schemes, it has some nice properties in that it's kind of more algebraic, right? Because you don't throw all this symmetric key cryptography in there to break all this beautiful algebra. So you can kind of do more stuff on it, and we'll look at some examples of that later. You can do Grosser-High proofs on this, and you can do hash proof systems on this. So it's kind of like you can do a lot more with these things. So I'm going to move on. So I'm about a little bit more than halfway with my time, so I think I'm good. I'll probably finish early. I'm going to look at an area which is kind of fun. It's password authenticated key exchange. Some of you probably know a little bit about this. Some of you know a lot about it. And over the years, there's a lot of different ways to solve it, but you can use hash proof systems. And there's been a lot of work from the early 2000s and even now just from this year on this. So it's kind of a fun application area. So instead of like doing like a broad survey of applications, which maybe there's not that many to begin with, but this is like one, I'll focus on this, which is kind of a fun application area. So this is an old idea that goes back to '92. This is initiated here. I'll put Villari, Poincheval, and Rogaway here. I guess they were the first to kind of actually give a nice formal definition of this. Although this is not I'll have more about to say this later. This is not a kind of a UC simulation style definition. This is more of a kind of the adversary plays a game and then he wins or loses, right? And you don't want to. There's actually some subtle distinctions between these two forms of definitions. And again, so I'll introduce the problem concretely in a minute. So, but it's very old, here's a partial. So, like I said, you can use hash proof systems. Some people do. There's some old work from 14 years ago. Katastrovsky and Young had a nice paper on this, which I guess according to Jean and Lindell, you could view it as using hash proof systems implicitly, perhaps. So they kind of formalized that. And then there's some nice work here that actually did this all, I think, in the UC framework. I think this is UC Secure. So, and there's a whole, I'm not being complete here. So I tried to like get the major things that I could think of. Okay, so this is like now for something completely different. I'm going to assume that some people don't know all that much about password authenticated key exchange, so I'll just introduce the topic. So one motivation for it is phishing, right? So people trick you into typing your password into a field in your browser, and you don't know where the password is going, right? So you could be sending it to somebody bad. So even if you had set up, a secure channel, this secure channel could be sending your password securely directly to, the bad guy, right? So phishing has been a problem for years and years and years, and PAKE is a way to solve this problem. And there's been reasonable solutions. I mean, '92, the problem was stated, and some solutions were given, and certainly by the late '90s, plenty of solutions were known, and just like everything else, none of it is used. So I don't know. But it's some nice work. It gives me an excuse to talk about hash proof systems. So and the first time I learned about PAKE, it took me like several tries to like understand what was the problem they were solving and why were they solving it and what were actually the rules of the game. So I'll give you my way of understanding it. It was just my own word. So the best way to understand it is just by looking at some things that don't work and why they don't work and try to see what it is you're actually trying to do, right? So in this setting, well, there are different ways you might start this out. I mean, let's just assume there's no SSL, there's no nothing, right? There's just you and the network, and there's just Alice and Bob in the network, and no cryptography, right? So I was going to use PW for password, but it didn't the typography didn't suit me. So S is the secret password. So S is the secret password. It's not a very nice letter, but it worked for me. So S is the password. So Alice and Bob are both thinking of the passwords, and they want to, do this without, and they don't want to be, they want to prevent. So in this particular solution, all it's trying to do is like prevent, well, let's see what it does. So Alice sends kind of a challenge response. Alice sends a random X from some large space, and Bob sends a random Y. So they never send their password over the wire, right? So that's a good thing. This password is never sent. And then they both can just compute a session key just by hashing, not using a hash proof system, just by hashing using some hash function. They hash their password and the two values X and Y, right? So let's look at what does this have any useful properties? Well, certainly, Alice is not sending her password to Bob, so that's probably good, right? What about an eavesdropper who sees X and Y? What can he do, he or she? Offline, okay, yes, everybody does this. So offline, so only so if Alice has a really good password, then there's really actually not much he can do, right? So that's good. But if so, here's the thing. So if after this they have this nice session key, and then if they didn't actually use the session key, you wouldn't have this problem, offline dictionary tag. So the problem only starts when you actually use your session keys, right? So Alice actually uses the session key to encrypt something, say, or to compute a MAC, right? And then and if the adversary sees just say one plain text ciphertext pair under the secret key, then he can run a dictionary attack, right? If he has the hunch that Alice's password is somehow easy to guess, then he can just take that one known plain text ciphertext pair and try all passwords S, plug into this function using X and Y because he's seen that, and then see which of those secret keys give rise to that same ciphertext, right? So there's only a problem when you actually use the secret key. So maybe you're just better off not using it. So this is susceptible to an offline dictionary attack. So this is when I was first learning about this stuff. It was kind of weird because it seemed to be like always changing the rules of the game. Well, I thought we were just trying to prevent phishing. No, now you're telling me an offline dictionary attacks too. So that's what we have to do. But we have to do more, right? So there's so here's one protocol that addresses the particular problem we just saw. An offline dictionary attack that can be carried out by an eavesdropper who can observe the network traffic, right? So here's an attempt at fixing it up a little bit. So now we're going to use a group, and we'll do some Diffie-Hellman type tricks here, right? So we'll instead of just sending X and Y, Alice will compute the group element X times P, and Bob will compute the group element Y times P, and they'll exchange Diffie-Hellman ephemeral keys. And then they'll both compute the Diffie-Hellman key, G to the XY, or which is X times Y times P, right? And then that's what they plug into their hash function. And just like in the spirit of ECIS and other such protocols, we'll just dump everything into the hash function. Probably you get by with just Z, but just to be on the safe side, we'll just dump everything here, X and Y and Z, right? So now look at our eavesdropping adversary. What can he do? Well, he sees, big X and big Y, and he's going to run through his dictionary, right? Plugging in S, plugging in X and Y, but what about Z? Well, unless he can solve the computational Diffie-Hellman problem, he'll never be able to even pick one, right? So he wants to try to make a whole bunch of hash queries. Hopefully all of them are relevant somehow, but unless he can solve the Diffie-Hellman problem, he can't make one guess at the password, right? So from now on, by the way, the best way to think about the problem is just assume that the adversary knows the secret key. That as soon as we compute the secret key, I just give it to the adversary. And now the adversary's job is to find my password. Instead of pretending that the secret key is secret, just give it to the adversary and now find my password, right? So this would be nice, except for the fact that this actually does protect against offline dictionary attacks, against an eavesdropping adversary, but it doesn't protect against what? Online. Well, all right, active attacks, right? Right. So Bob here could be the bad guy, and he just runs the protocol with Alice, and so he actually knows this little y. And so he can compute Z, and that's it, right? So if you're on the outside looking in, you can't break this. But if you're on the inside playing against Alice, carrying out some kind of, say, phishing attack or something, then you can actually interact with Alice. And once you run once bad Bob runs the protocol with good Alice just once, he can start his offline dictionary attack, right? So what we want to do is to be able to prevent this even from an insider. And this is a nice, I think it's still the simplest possible protocol that you can prove secure. It's in the random oracle model using a hash function. It's by Abdallah and Poincheval from 2005. It's really slick. It's almost the same, except now we have two public parameters A and B, and we kind of somehow mix together the Diffie-Hellman thing we take our password itself and view it as a scalar, and we use that to multiply by these public parameters, right? So even if you see big X and big Y, you can't really start doing anything right away, right? Because you don't actually see X and Y. You see X and Y kind of masked by this group element here, which itself depends on the password, Yeah? And you can actually prove a nice little lemma that says that while you can make one query, you can't make two. So if you can make two queries that are somehow relevant with the right x, the right y, and the right z, then if you can make two such queries, then you break the CDH. That's basically the theorem. But of course, this is all of this kind of only makes sense in the random oracle model, I guess. That's it. I'm not going to, it takes some work to kind of digest this protocol and certainly to begin proving security about it. But I think it's a pretty cool protocol. So that actually gives us a really practical protocol that works. As far as I know, nobody even works in the random oracle model, and I don't think anybody implements anything like this either.
So do people actually use this? Or?
That's what I'm saying. No, nobody uses anything.
Is there something more efficient which is not broken?
I don't know. Does anybody know? Are there even like symmetric things that avoid kind of public key crypto like this?
Let me say something.
Yes, sir. Oh, yeah. You're okay. Right.
Something practical.
Yeah.
I represent practice.
Yeah.
I mean, these symmetric pairs are not what you need in real.
Right. That's another issue because you don't want right. So a big problem with all of these schemes is that the server, if Alice is a client and Bob is a server, then if the protocol actually requires both of them to know the password as input, then of course if the server is compromised, then that's considered bad. So this is actually worse than, in some sense, these protocols are worse than, but there are protocols that avoid that too, right? So, and that aren't much more expensive either.
That's what he said. There will be adoption of this protocol in the next few years.
Oh, you're working on that?
Right now you stand that you do everything over TLS, and you assume that you have a public key of the server.
Yeah, but there are still phishing attacks that can, if you're tricked into, you can be tricked into, like I said, you could send your password securely to the bad guy even with the golden padlock in your, so.
You have to deal with phishing attacks in a different way.
Yeah, I know. Well, okay, fine, all right. So we can.
So Victor,
Yes, sir.
so what Hugo was asking is that the server knows the hash of S or something like that in order to transfer it. Like a,
Right. Yes, but you can easily you can. There's a simple modification of this protocol that this was actually in a paper I wrote with Ike Kiltz and others that the server just stores the hash.
or GTS or something.
Yeah, something like that, or just G to the S. Yeah, I mean it's G to the hash of the password. Yeah, something like that. Yeah, you just store G to the S. Mm-hmm. Okay, so but now, just because we're talking about hash proof systems, we can talk about how you can do without random oracles, what you can do with random oracles using hash proof systems, right? And the structure is going to look a lot the same. So there's a whole line of papers. I already mentioned a couple of them that started out in the early 2000s, and this one by Jonathan and Vinod is probably the most simple and elegant. Although, as I'll discuss, they need some extra requirements for some of the primitives, the building blocks, to get a protocol that's simple, and then some follow-on work has shown how to actually realize these building blocks in quite efficient ways. But from a high-level protocol design, it's really simple. So here's Alice and Bob. They're both thinking of their secret passwords. So now we're using hash-proof systems, right? So we have our keygen. So Alice is going to, so actually in each protocol, so unlike the public key application, where the public key for the hash-proof system is kind of the long-term public key of the encryption scheme, these are all going to be ephemeral. Everything is ephemeral here. So every run of the protocol, Alice is going to generate a public key secret key pair for a hash-proof system. Okay, more setup. I'm skipping ahead a little bit too much. So this is in the common reference string model. So the public parameters of the common reference string will require a public key encryption scheme, and it should be a CCA2, Chosen Ciphertext Secure Public Key Encryption Scheme. And we're going to need a hash-proof system. Oh, yes, right. I'm jumping ahead. So, right, so we'll need a hash-proof system for the language consisting of all valid ciphertext plain text pairs. So the language is the pair of all CM, such that C is a valid encryption of M. That's the language. Yeah? And so the witnesses will be the random coins that, it's a probabilistic encryption scheme, right? So witnesses will be the random coins that go into the encryption process, okay? So that's our language, and we assume we have a hash proof system for that. Okay, so then Alice is going to generate a PK-SK pair for the hash proof system. She's going to encrypt her password. Now, this is just one of those goofy, encrypt your secret to a black hole kind of thing, right? It's just a system parameter. Trust me, nobody knows the secret key. It was generated by NIST, and nobody knows the secret key. So go ahead and encrypt your password. She does. And I guess it's good, right? We could built in, I guess the NSA would really like this, right? So then Bob does the same thing. Everything here is symmetric. Bob generates a public key secret key pair for the hash proof system and encrypts his password, right? So Alice encrypts S and gets ciphertext C. Bob encrypts S and gets a ciphertext C prime. Then they exchange their public keys for the hash proof systems and their ciphertext. So Alice sends to Bob her public key for her hash proof system and her ciphertext C. And Bob does the same thing going back to Alice. They can do it at the same time, one flow, and that's the whole protocol. What is their secret, their session key? Their session key is this. So it's the hash of C prime. So, right, this is supposed to be ciphertext message pairs. So here's a ciphertext C prime and S. C prime came from Bob. I should have maybe had Bob subscripts here instead of primes. And Alice, and this is Alice's secret key, right? And then it's symmetric. So using Bob's secret key, we can hash Alice's ciphertext. So just to go and to show you then how the computation actually works, then what is Alice doing? Alice, from Alice's point of view, she generates PK-SK and generates a ciphertext. She knows the witness for the ciphertext. She knows the coins that went into it. She sends all this to Bob. She gets this PK prime C prime from Bob. She has no idea if they're really what they're supposed to be. She uses, so she doesn't know Bob's secret key. This is Bob's secret key. She doesn't know it. She uses her public key and her witness, right? She generated the ciphertext. So she knows the witness, and she can use the public key that Bob sent her. Bob has kind of the symmetric view, right? He gets PKC from Alice. He uses his public key to generate this because he generated C prime and knows the witness. And he uses his secret key and pushes Alice's ciphertext through his hash function using his secret key. Yeah, so that's the whole. So proof of security, hand waving. So let's just look at, say, Bob's point of view. So let's say Bob is, I think for these proofs, we're pretty much always in the static corruption model, and I don't even know what model we're in, because I don't know if we're in the game playing model or the UC model. It doesn't matter. We're in the hand waving model. So from Bob's point of view, what does he see? So let's see. So let's say Bob is honest and say Alice doesn't know the password, right? So she sends something. So clearly, this is supposed to be a proof that Alice's ciphertext encrypts the password, right? So by rights, if Alice doesn't guess the password, this proof will be invalid, right? So it'll be a random looking group element, right? From Alice's point of view, it'll just be random looking, right? She has no idea. She's handed Bob this ciphertext, and when Bob hashes it, it turns into some random group element. Yeah, so, and it doesn't matter really what Bob does here. From Alice's point of view, this is the random key. So this gives you, so what does this give you? If Alice is trying to, play live with Bob and trying to, make an active attack, online guessing attack, if she guesses wrong, then Bob will start using a random key, right? And so presumably the session will quickly die, right? Because so it doesn't have explicit authentication. It just has kind of implicit authentication. Any questions? Yeah.
Statistically hiding commitment rather than in.
No, this is it, man. This is it. There's nothing hidden here. What? Oh, what? Yes. Oh, can you? Oh, I thought you were asking if there was more to it. No. Yes. Right, depending on what you want to prove, right? If you want to ultimately get UC security, you definitely need some kind of encryption to encrypt to your simulator. And I believe you can get by with some kind of a commitment as well.
And then you don't give your secret to anyone.
But you can't be
But-
statistical, because otherwise it won't make sense, because then everything will be in the language.
No, to create
Also,
C.
the secret key,
C is
it
a commitment,
changes
statistical
sometimes.
commitment. Not an encryption, simply statistical commitment.
I'm only a spectator when it comes to password authenticated key exchange, so you can ask the experts offline afterwards.
Is it enough? I mean, no, you need CCA. Do you need CCA?
Well, you definitely need CCA security. Yeah, I should say, when I said there's nothing more to it, I was lying, actually. The one thing I'm lying about is that we need CCA security with some kind of labels or tags, because you have to have some way to, again, it depends on with your UC, whatever. You need some way so that, ciphertext from one session can't be replayed in another. So, and for that, you need CCA security to ensure that, you can embed a label of some kind that identifies the names of the parties, the session ID, some kind of stuff. You just put that all into a label, and then you labeled CCA security, and that'll prevent replaying one ciphertext from another, and that's kind of what you need to make the proof of security work. So that is one, yeah. In fact, for all of the things I presented, even the earlier hash-based systems, you should embed identities and such into the hash function. And here you definitely do embed it into the encryption. So that's one simplification that's actually important. Okay. So moving on. Okay. So what we'll do here is we'll just plug in classic Kramer-Shoup encryption. I said it was good for something. What it's good for is you can use it to prove things about it. So what we want is a hash proof system for this language of plain text ciphertext, right? So let's look at what the issue is here. Here's what a CS encryption looks like. There's a group element x1, x2, and y and z. So if it was encrypted properly, x1 is w times group element L1, g to the x, if you like. x2 is w times L2. When is it an encryption of the message M, the password in this case? Well, y times M should be w times A, where A is part of the public key, right? And Z should be this funny, mangled, too smooth hash proof, right? So it should be WB plus WTC. So L1, L2, A, and C are all, system parameters. They're all fixed. And T is this funny hash of X1, X2, and Y. So T is going to vary from encryption to encryption. Now, I might have misunderstood something when reading some of these old papers, because some of the newer papers simplify things greatly. So this is the implementation issue. As a language, the language itself it depends. If you view T as fixed here, then it's just a kind of a generalization of the one-dimensional Diffie-Hellman problem, right? It's just one dimension. You have a vector of group elements, and you're looking at scalar multiples of that vector. But if it's, so you could just solve that problem using almost the same hash proof system as before, right? But a problem that arises here is that actually T is not fixed. It depends on the ciphertext. So some of the older papers from the original papers on this work added an extra flow, because you had to wait until you saw the ciphertext before you could prepare even the public key and the secret key for the hash proof system. So there was an extra flow. And some of the later work from just a couple of years ago made a nice observation. I think it was a new thing, I'm not sure, but it's actually just and kind of showed where a first step where you could go with some of these hash proof system ideas. You could you can do a language. So doing it with the T kind of defining the language is okay. It just causes an extra flow. So if you really want to be minimalistic on flow, you can do the following. We can reduce this to. So in some sense, if you view the language is including T as an instance of the thing you're trying to determine as a language, that's varying. If you want to reduce this to another subspace problem, where T doesn't have to be fixed for all time, then it's a simple reduction. So here's what I mean. So you have x1, x2, y minus m, and z. So the problem was with this z. Z was supposed to be this mixed this inner product-like thing here. WB. So here it was WT times c. So suppose instead of working with vectors of length 4, I move to vectors of length 5, and I'm going to work instead of in one dimension but two. So then if I want to know the answer to this question, I just reduce it to an answer to a different question, where this new question doesn't depend on T. I mean, the question depends on T, but not the language, right? When you do a reduction like this, I guess I have an instance that I want to know whether it's in the language, right? And I do a reduction to another language, and that maps the original instance to a new instance, and the original language to a new language. And maybe you can do it so that actually the language doesn't depend on the original instance, in which case I won't get this extra flow in the protocol. So the new language is just so just don't look at this line once, just look at this line. It's just all tuples of this form. That's the language. So that's a subspace problem of dimension 2. Just like the D, like you saw on the D-Lin example, you can write this down as a pair of generators in the ambient space of dimension 5. It's a subspace spanned by 2 vectors, so it has dimension 2. And then to answer the original question, I take the same 4 group elements that are here and just plug T times x1 in here. Right? So you send me a public key for hash proof system for this language, which doesn't depend on T, and then I can evaluate it. Either one of us can evaluate it now by just plugging in T times x1 for this in this first slot. And then you see if T times x, so if x1 is w times, let's see if we can do this. If x1 is w times L1, then I guess T times x1 is T times w times L1. So just repeat that to yourself. If x1 is w times L1, then T times x1 is T times w times L1. So that means V must be T times w. So that gives us what we want. Yeah? Anyway, I don't know. You guys can just tell me if I'm wrong. I don't understand why there was always an extra flow on these old papers, just because people didn't know like this kind of a trick, or I don't know. I really don't know. It seems like anyway, that's just it. So it's nice to see that a simple idea can solve kind of a problem that's been laying around for a long time. Just a simple reduction and then moving to a higher dimension. There's another implementation issue. Okay, yes?
You're saying this to work with the cards? I mean, we needed an extra flow because...
right, that's the implementation issue number 2, actually. But even in the older papers, though, there was sometimes an extra flow also, because even if you weren't right, it's a UC simulation issue, right? Which I'm going to talk about next. But even without the UC simulation issue, if you're just going to get the Bollare, Poincheval, and Ragaway, is that the R? Huh? Yes. Even if you want to just get that definition, you were kind of stuck with an extra flow if you didn't use a trick like this. Yeah? So, because you couldn't, right? You don't know the language until you see the ciphertext. So it leads to an extra flow. But you raised the question of implementation issue number 2, which is only if so you have to be a real kind of, UC geek to appreciate this stuff, right? So just looking at the protocol from Alice's point of view, and again, static adversaries, Alice is honest, right? So, what does honest Alice do? And she's talking to bad Bob. She sends an encryption of her password. And then she evaluates this. And this is, right? And she uses Bob's public key and her witness, right? Now, if you try to do some kind of simulation proof here in the UC model where you have an ideal functionality for testing if passwords are equal, of course, the simulator at some point is going to have to take over Alice's job here of sending these messages on the network, right? And so what she's going to end up having to do here is encrypt garbage without knowing the password. And then somewhere else in the simulator, it's going to actually, this is where you want to use CCA security, is actually going to decrypt the ciphertext that Alice receives from Bob and test whether or not that guy is a valid encryption. If it is a valid encryption of the path, then you can ask the ideal functionality, if it's equal or not. If it's not equal, fine. Then you just pretend the session key is random, which is what would happen in the real world. If it is equal, then if you're working under the BPR definition, the game is over anyway. The adversary is won, and you can bound that the probability of guessing the password is no more than it was a priori, right? But if you're a UC geek, you have to keep going, right? So Bob's guess may be correct, in which case you have to answer with something. And if you answer with the wrong thing, bad Bob will see it, right? So the show must go on. Even if Bob guesses correctly, you have to keep going. And I think there's still some, I'm still confused by all of this, because in the BPR definition, if you have 1 million users and one person has a bad key, a bad password, an easy to guess password, doesn't that, like, the proof doesn't let you, these proofs of security don't tell you anything about the people who have hard to guess passwords. But maybe, which is why the UC simulation definition seems, I mean, of course it's better, but I mean, of course it's better also in the but it seems like there's something still in between that one could hopefully prove. Because there's a big gap between BPR and UC, and it's not clear to me that there's not something in between that's more, that's still useful and gives stronger security stronger security guarantees of BPR. So the show must go on. So here's, Right. So what we need is some kind of simulation soundness, same kind of tricks that people have been using for 20 years, right? Simulation sound. So this hash proof that Alice wants to send junk, but then she also has to send a hash proof on that junk, but she can't really do it anymore because she's in junk. So she needs, there's already, there's a public key and she's using Bob's public key, right? For this. Bob has a secret key, but what Alice needs is her own super secret key, right? That will allow her to create a hash proof system using the super secret key that Bob doesn't even know, right? So, and that's kind of like a simulation soundness thing. And OR proofs are a way that people in many different contexts, ordinary zero knowledge, interactive zero knowledge, non-interactive zero knowledge, kind of proving an OR of two statements is kind of a traditional way you can achieve this kind of cheating ability of a simulator, right? So instead of like proving that this ciphertext is an encryption of my password, I'm going to prove it's an encryption of my password, or that I know the secret, right? And I don't know the secret. Only the simulator knows the secret. So the simulator can prove this, one of the two, what do you call them? Disjuncts, and the real person can prove another, right? So right now, so I'm going to just ignore everything I've just done and just talk about OR proofs for just a couple of minutes, just for fun, because it's a general tool that solves this problem, and another, they're kind of cool anyway, and you see them over and over. So, but we can do hash proofs of disjunction, and this is nice work just from the last couple of years. So here we want with the languages now. So we have two languages, L1, L2, and now I want to construct some kind of a hash proof system for pairs x1, x2, where x1 is an L1 or x2 is an L2. Yeah. And then using this kind of thing, we can do one-time simulation soundness and all kinds of cool stuff. And these guys, did all this stuff the last couple of years, and there's lots of more efficient PAKE, some new things called IZK, what's the I stand for? I don't know. Group PAKE, threshold, there's lots of stuff. So because you guys invited me to this, I tried to read all these papers, and I found it interesting, so I'll share with you one tidbit of interesting things I learned over the last week preparing this talk. So it's fun and it's easy. So DDH, right? So we're given two vectors in this, two vectors. Each of them is 2 elements long, right? So we have the usual DDH problem, and we're given two vectors, test vectors, x1 and x2, and we want to know, is this first x on the line spanned by this first L, or is the second one spanned by this line? Yeah? Right? And in the hash proof system jargon, a typical user will just have a witness for one or the other, but not both, right? And they'll want to be able to want to set up a hash proof system for this. Now, there's an easy way to do this and a hard way to do this. I'm going to show you the easy way to do it. The easy way has a disadvantage. It doesn't really solve the problem that I set out to solve, which is kind of having this one flow thing. This is going to add flows, right? But OK, there's a harder way to do it that adds flows, but that's less fun too. The easy way to add a flow, and anyway, this is probably useful. So we're going to translate this OR problem into an ordinary subspace decision problem. And it's just beautiful and simple. So and maybe it's kind of already appears in other work. So this is a matrix. The rows of this matrix are going to be the generators for my subspace problem, right? So, this is going to add a flow. Right, the reason this is going to add a flow is that now I'm back to taking my instance x and embedding it into the language that I'm defining. So that invariably will add a flow to these protocols. So that my matrix is going to actually, and then the new instance is just a constant. Okay, so I got these 4 generators, L, 0, minus x, 0, 0, L, 0, minus x. And then I cleverly add this column over here. Yeah, and the target, right, so the language is, the things, all vectors, each row vectors, I can look at linear combinations, right? So the language is all row vectors that can be expressed as linear combinations of these rows and giving me this. So how do I get this? Well, you see by the clever placement of 0 and p here, the only way I can get a p here is to pick either a p here, either pick this row or this row. I can't, right? I have to use non-zero scalars there. And if I say pick this one, then the only way I can get this guy to hit 0 is if I actually, right, get a linear combination, or this could more generally be a vector space set of generators, but this guy has to be a multiple of this guy because I have to get cancellation to get a 0 here, right? So I could pick p, I could pick this row, and then I have to pick scalars here, or I could pick this row and pick scalars here. If I have both witnesses, I'm feeling generous, I can also come up with a 4, right? So here's my advanced LaTeX here. So if I have so I say I'm in the first, if x1 is in the first language and I have a witness for that, right, then these would be the 4, this would be my witness. So I would get W1, 1, and that'll hit this guy, right? And if I'm in the second language, then this is my witness. And that's it. And if they're both in the language, then I could actually have 2 different witnesses. Which is actually interesting because the whole point of OR proofs, and I haven't said this yet, but the OR proofs are useless unless they're witness indistinguishable, right? I can't do any of this unless I can be sure that the bad Bob doesn't tell if I'm using one witness or another witness, because that was the whole point, right? And all the hash proof systems that you've seen so far have had the interesting property that the set of generators that were linearly independent. But these are invariably going to be linearly dependent. And the issue is, so like I said, we need witness indistinguishability. And it's true that it is witness indistinguishable, provided the public key for the hash proof system was generated honestly. If it's not, then just generating the public key on that guy could leak information about my witness. So, right? So here, and and this is all, this is just math, there's no cryptography here, right? So what does it mean so this is my matrix, and here's how, right, so like I said, you just take, the secret key is always just a vector, and I take inner product, so I can make that as a matrix vector equation, right? So if this is my secret key, this is my public key, right? And what's the property that a public key has to have to be valid? Yes. Huh? No. Oh, no, the matrix is fixed. So the matrix is fixed, and we all see it, and you give me a public key, right, which is supposed to be of the form matrix times little a, and you give me this, right? Yes, you're on the spot, Daniel, so I'm picking on you. So.
In the row span of that matrix.
Row span?
Column span.
Column span, right. I'm trying to prove that a certain vector is in the row span, right? But before I prove it to you, I'm going to demand that you give me a vector in the column span. And that'll be sufficient to assure that this is actually witness indistinguishable as we need, right? So the rows of the matrix may be linearly independent, which means that not all columns are in the column span. For the other examples we looked at earlier, they always were, so there's no issue, right? So the verifier, so I'm the prover, you're the verifier. I want to prove this to you. You want me to prove, I don't care, but I want to prove this. You want me to prove this to you. But you give me a proof key, a public key, and before I touch that thing, I want to make sure that it's actually valid, right?
There's a problem with dishonest verifier. Honest
right, but everybody's dishonest, right? We want to this is bad Bob. You're bad Bob, right? You're bad Bob. I'm honest Alice, and I want to, before I use my public key to evaluate anything, I want to make sure your secret key itself is, I want to make your public key is valid, which means that this vector that you give me should be in the column span. And how do you do that? Well, hash proofs, of course. It's the same problem. Now you might think, well, before I can prove to you that my row is in your row space, you have to prove to me that your column is in the column space, so maybe we go back and forth forever like this and it never stops. But actually, it's not true. By adding yet another flow, you can do this very easily. Because you want to prove something to me. I want to prove something to you. And you have to prove something to me first before I prove it to you. I have a real secret, but your secret you don't really care about, right? I want to prove something to you using hash proofs. So I'm going to have, so you're going to set up your own, I got this backwards. This is the last slide, really. So Here's Alice. So what did we say? Bad Bob. And I want to prove something. This is the prover, right? So you send to me a public key for a hash proof system, and I don't know if it's valid or not, and I don't want to touch it until I do, right? I want to send to you, so I want you to prove something, right? So I send to you a public key. Here's an easy way to do it. A public key prime. I have a secret key prime, right? And it's a hash proof problem, right? Right? So I want you to send me back a proof that your public key is valid using my PK prime that I just sent you, right? But you don't know if my public key is valid, right? But okay, you send me a proof, pi. Yeah? And maybe you've just blown everything here, right? Because, but then I just send you my secret key prime. I don't care about my secret key. It's just I'm just using it right now. And yeah. So I think this would work. This is simpler than what you guys do, but it adds more flows. But there's a way to do it without adding flows that uses a bit more computation. You expand the dimension a little bit. But I think this works, right? So I just, I'll talk about it with you offline. But this is the only thing I could come up with because I couldn't understand what you guys did. So that's what I came up with. But it has more flows, so it's not good. There are other applications. So there are oblivious transfer. There's some stuff from a while ago, and there's some even new stuff I don't understand, but this is all, I haven't looked at it yet. There's some cool stuff on leakage resilience. These guys, this is just one paper with lots of authors. They have something on language authenticated key exchange, which uses this stuff. So lately, and then HOTEC and I don't know much about either one of these papers. There's some stuff on key-dependent message security. So there's lots of different applications, and I'll close. That's about all I have to say. I mean, one other kind of philosophical point or just takeaway point is that, maybe understanding all the different gadgets and widgets and tools that are available, where do hash-proof systems fit in? I mean, I'd say they're kind of the cheap and lightweight brethren of Gross-to-High proofs. When they work, they work great. They're limited. Their application is limited, right? They're kind of designated verifier proof systems. They only work for simple linear type languages. But when they work very well. You don't need pairings and all this stuff. But if you need to do something more complicated, you can do Gross-to-High type proofs, and then above that is kind of general purpose tools. So anyway, I thank you. This was a great experience for me to actually read some of these new papers, which I would never have otherwise read. It's a great tonic for my deadwood syndrome. So anyway, thank you very much. Any questions?
So all the examples were for these linear type languages, but there's no reason why it should be, right? I mean, for instance, you could potentially have a hash proof system for graph isomorphism, although I don't know.
Yeah, I don't know either, right?
There's nothing. I mean, there's an upper bound saying all the languages that you can do hash proof systems for are in statistical zero knowledge.
Well, then didn't you said the student worked on some stuff that suggested a. That's it, witness encryption, which I guess is similar, but of course that's all at the level of that's very expensive. It's the same thing? I see. But of course the interest is in problems that are actually much harder, and so the solutions are very...
the guaranteed smoothness is computational?
Yeah, you can make all of these. People have done, you can make all of these things computational as well, and then maybe it's the same thing. But of course, if you want to do it for really interesting languages, then you very quickly, you get, I don't know about that. What can you do? Anything?
That's witness encryption.
You can do it for anything in NP, right? Anything in NP.
But you need big tools for that.
But you need big tools, I/O, right? So, yeah, this is all low tech. That's high tech.
The Krimish, the El Gamal example, the first example of public encryption that you gave. I mean, so the more general statement is that if you have an average case hard language with the hash proof system, you get public encryption.
Right. That's correct. Yeah, that's all. That's all there is. Yeah. Any more questions?
Like this. Hash proof systems, you can sort of view them, and you explain them that way as a sort of a proof system that has a statistical guarantee, right? Like it's sort of a witness indistinguishable or beyond its verifier zero-knowledge proof system and the statistical guarantee. If I didn't care about that, if I allowed computational, could it be easier to do?
I don't know. I mean, we just did it this way because we could, and I don't even know if there's a. I mean, yes, you could certainly define it, and I guess it has been defined, just given a different name, and then, you know, that'd be perfectly fine. It just seems like this is what we're able to do. So it'd be nice to see if there's like something in between where you could do it without too much
Right, or maybe
overhead and.
general language that's,
Yeah.
But for some of the applications, you needed the statistical guarantee.
Oh, yeah. I mean, sometimes it's very convenient. Yeah, yeah. I think sometimes it is convenient to, for certain types of proofs not. I mean, proving security that it can be convenient. Certainly not for the basic encryption thing. No, that could be all. For the basic semantic security and even CCA2 encryption, you could do all of this with computational type assumptions.
Yeah.
Any other questions? Okay. Thanks again.